A comma B and plus capacity of C comma D. Okay, so we have only two edges which are coming out of capital S, which is S comma B and C comma D, but not AD. AD is going into S. So sum up their capacities. So in the next line you will have answer. Okay, in the right. So C of AB equal to 1 plus CD 1. That means 2. So what we can see, that is uh, statement 1. Now we have find that we find that C of S comma S prime is equal to maximum flow. Hence S comma S prime is a minimum cut, which is statement 3 of the theorem. Okay. Next we consider the second statement. Second statement, which is we have already solved here. Uh, augmenting path available for the residue in the residual network of GF of G. So this is the statement 2 on the system. So hence in this example we have verified the minimum. Oh, uh, we have verified the maximum flow minimum cut theorem. Okay, so I wanted to actually show you the proof of this very popular and very very hands-on theorem, maximum flow mean cut theorem. But let's see, we will skip that proof, and if time permits later on I can show you the proof. It's very good proof. Okay, so let's move on. Let's close this, the maximum flow mean cut theory. Okay, here, and go to the next topic, which is very benchmark problem, matrix chain multiplication, which is a very good dynamic programming solvable problem. Okay, so um, so what is the problem? Matrix chain multiplication. Uh, in matrix chain multiplication, what do we mean by this problem? We take up one example. Okay. So given a sequence of n matrices, suppose we are given so I hope everyone can see me, right? Fine. So suppose we are given a sequence of n matrices like A1. Okay, okay, so A1, A1, then 2, A2 dot AN. To yield, compute a matrix product like this. Okay, where we have A1 dot operator into A2 dot AN. Okay, so we want to compute this product. So, and we are given a sequence of A1, A2, N. And you know, it's a sequence of n matrices, because n matrix multiplication is not commutative. That's why the order is important. That's why we are talking that it's a sequence of n matrices. That means it's an ordered set. Okay, it will matter if I change the sequence. If I shuffle the positions of the matrix, it will be a different meaning, right? So it's a sequence. So as matrix multiplication holds associativity, all possible products are same. Okay, means we want to mean that. So if we have, okay, so here we have A1. Let's say we are given A1, then A2, A3, then A4, and that's all. Four matrices we are given, and we want to put here a bracket. Okay, here we put a bracket. Here, now we put a bracket close, bracket close, bracket close. So you can understand that. So we have three bracket opens and three corresponding bracket closes. Okay, so this here we put a bracket over here, and then A2, then A3, bracket close, A4. In this case we have A2, A3, then we will get here bracket close. Okay, so here we similarly have, okay, let's delete this. Right. Okay, so let it be A1, A2 first, A1, A2, then A3, A4. Okay. this. Here we have A1, A2, A3 first, then overall. Then we have A1, A2 first, then we do with that A3, okay, and then overall with the 4. So you can see now we have 4 cases. If you have any question, please ask me after this. Okay. Otherwise, you know, you will feel bored. Okay. So we have this is a very it's a benchmark problem, but the main important part is most of the visualizations are hidden, but you have to visualize the hidden parts in this problem. That's the major challenge of this problem. Okay, so this problem will is tackling a very large issue. Okay, that's why you need to visualize properly what is the actual issue. So see, as the matrix, so this, see, we are computing the product of 4 matrices A1, A2, A3, and here we have what we have shown. আরেকবার বলতেন যেখানে আনডিরেক্টেড এস থাকবে রেকর্ডেড ভিডিওতে স্ক্রিন দেখা যাচ্ছে না ওকে okay I will come back to that portion later just for the time being you consider here so so see first we are computing A3 A4 then the result A3 A4 is mm, multiplied with A2 then A2 A3 A4 is multiplied with A1 so here the sequence is A3 A4 then the product is multiplied with A2 then that is with A1 which is not same in this case A2 A3 first then that product is multiplied with A4 then that product of 3 matrices is multiplied with A1 here A1 A2 first then A3 A4 then the product of A1 A2 and A3 A4 here A2 A3 that is producted with A1 then it is multiplied with A4 so all these are the all possible 5 sequences of multiplications okay so these are the 5 distinct uh, sequences of same matrix product A1 dot A2 dot A3 dot A4 okay so all of them will give us same result but why we are considering this sequence of matrix multiplications somehow the sequences are different so does that matter the different sequence will should we actually consider the different sequences separately yes how let's take an example let A okay let A have dimension 10 cross 30 then B has dimension 30 cross 5 so 30 cross 5 then C okay have 55 cross 60 B has Okay, so let's consider these three. So it is sufficient to compare at this moment the sequences. So what we want to have, we want to do here, first A multiplied with B, then that is C. Okay, and then we do here first BC, we will multiply A with that BC. So both are producing same matrix product, but let's say here what we have, while computing AB first, the number of matrix scalar multiplications involved are, so A is of dimension 10 cross 30 and multiplied with B 30 cross 5. So if I do compute AB, that means the scalar multiplications, number of scalar multiplications equal to 10 into 30 into 5, and that is equal to 1500. Okay, so this is for the AB. Then plus we are computing, so the resultant matrix becomes AB, of which dimension will be 10 by 5, 10 cross 5. Okay, that 10 cross 5 matrix AB is getting multiplied by, here we can write here, right, here we can write, so this is 10 cross 5, right, and C is of dimension 5 cross 60. Okay, so at this moment if I do that, 10 cross 5, that means now AB is multiplied with C, so 10 into 5 into 6, 60, 10 into 5 into 60. Okay, so this many number of scalar multiplications we will have. Okay, then in the next line what we can write, so this is equal to okay, let me write here, say right here, the first is 1500 and the second one is 3000. Okay, so in the next line this is 4500. Okay, and what about this ABC? Can you compute the number of scalar multiplications and get me the result? So please try to find out and get me the result, how much it is. Please calculate for me the result, number of scalar multiplications for this case ABC, how much it will be. So it will come out to be actually 7000. Okay, so ABC is faster than A matrix chain multiplication. The problem to find which one, A into BC. Oh, right. Okay, this is nothing but the ABC. So while computing ABC, where AB is computed first, then the resultant matrix is computed with C, multiplied with C. So the total number of scalar multiplications we want to find out. Okay, this is 550. So here first is while multiplying A and B, so A is having dimension 30, 10 cross 30, B is dimension 30 cross 5. So total number of scalar multiplications 10 into 30 into 5. So 10 into 30 into 5. Okay. So and if I compute the product AB, so AB product will have this dimension 10 cross 5. That is getting multiplied with C of its dimension 5 cross 60. So computing this product, we have scalar multiplications 10 into 5 into 60. So 10 into 5 into 60. So then it is coming as 4500. Okay. Okay, understood, sir. Just try to understand, make yourself convinced that for any matrix, for any matrix A and B, let's say while computing the product AB, where A is of dimension 10 by 30, B is of dimension 30 by 5, the number of scalar multiplications involved to compute the product AB is 10 into 30 into 5. So I hope you know this. If you don't know this, you just try to understand it by taking an example. And even if you can't understand this, just ping me, I can give an example demonstration. Okay, so ABC faster than, that means A into BC, hence sequence is mattering. So matrix chain multiplication is a problem to find a sequence is optimal, that is solved with minimum number of multiplications. Okay. In other words, the problem is to find optimal parenthization. Okay. Okay. So parenthization means this one, parenthizing. Okay. So how can we parenthesize the matrix product like this? First AB, then C, or first BC, then A into that BC. Okay, so it's a parenthesization problem, and the problem is to find optimal parenthesization by means of finding optimal sequence to achieve minimum number of scalar multiplications. So this is the problem which we are talking about. Okay. Okay, so now let us now move on to understand the problem statement mathematically. Mathematical understanding of the problem statement. Okay. So given of n matrices, Okay. So given a chain of n matrices, uh, okay, with matrix dimensions, with matrix dimension of I think better we can move on to, that's fine, I as pi, it is ith pi minus 1 cross p sufficient a suffix I. Okay, so this is where for all I 1 2 dot n, ঠিক আছে? Product 1 dot a2 dot a3 dot an is parenthe in such a way that minimizes the number of scalar multi. Okay, now let be the number of alternative parentheses of a given sequence. Let us denote this sequence to be as uh, okay. So let us sequence P. Okay. So the sequence is a1 comma a2 comma dot an, or a1 dot a2 dot a3 dot an, and so on. Okay, so that's the sequence, and let us denote that sequence as a P, and Pn is the number of alternative parenthetizations for a given sequence. Just take an example and try to understand. I mean, these are actually prerequisite, so it will probably will take some time, but okay, fine. So take an example. Example means what example we can take. Uh, what example? Okay, so let's say we have a1 dot a2 dot a3. This is my a sequence P. So for this sequence, how many alternative parenthetizations we may have? Okay. So we have already find that for 4 matrices, that is 5. So for 4 matrices, a sequence of 4 matrices, we have 5 distinct sequences. Okay. So in now talking about parenthetizations, let's see. I use this parenthesis a1, then a2 dot a3. No need to provide dot. Okay, a2 a3. Okay, we have to provide dot. Okay. So if I provide parentheses, if I do not, if I I mean, um, if I put parentheses on A1 itself, here we are not providing parentheses like this because it's a single matrix. So no need to put A1 into inside a bracket. Okay, so no brackets are there means A1 is parenthesized. Okay, so if I use a parenthesis to a single matrix, then how many parentheses we have to use for the remaining part of the sequence? In this case, A2, A3. So here we have parenthesis 1 and the outer parenthesis, that is 2. So here the number of parentheses P3 equal to, okay, for this example only, this kind of parenthesization, we have the number of parentheses involved 2. But another parenthesis in example here similar to this one, so this, okay, A1 A2 first, A1 A2 first, then it is multiplied with A3, right? So it involves P3 is equal to again 2. Okay, okay, so first we compute A2 A3, one parenthesis, and then the product is multiplied with A1, second parenthesis, so P3 equal to 2. Again we may have, for this case, A1 A2 multiplied first, one parenthesis, then the product is multiplied with A3, so second parenthesis, so P3 equal to 2. And we do not have any other parenthesization possible. These are the only two possible parenthesizations for three matrices, given three matrices. So what is the total number of parenthesizations then? So this is, so ultimately P3 becomes equal to 2 plus 2, which is equal to 4. So this is your Pn, the number of alternative parenthesizations of a given sequence. So a given sequence may be parenthesized in many forms, and for all the parenthesization you have to calculate the number of parenthesizations and sum up them. You will get the total number of alternative parenthesizations for a given sequence P. That's what I mean to say. Okay, so now see, when n is equal to 1, okay, Pn is equal to 1. That is very clear to understand, because we have only a single matrix and that requires just one parenthesization. Okay, so we can initialize Pn equal to 1 for n equal to 1. And when n is greater than or equal to, okay, greater than or equal to 2, then what we can understand that Pn, okay, let me equation format. So then we have Pn is equal to, okay, so what we are doing for this kind of problem, here we have an example. Let's say we have A1 dot A2 dot A3 dot A K dot A K plus 1. Okay, K plus 1 is not in the bracket, it's in the suffix of A. It means it's K plus 1 matrix A. And then dot 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 an. Okay, so we have n number of matrices multiplied to be multiplied. And where should I, and let's say we want to, okay, one thing you understand, that three matrices can't be multiplied together. Only I have to, take a pair of matrices, only two matrices, then multiply them, then get the product. That product have to be multiplied with a third matrix, so as to get a product of 3. That product of 3 will be again paired up with fourth matrix, okay, for matrix multiplication. So for doing matrix multiplication, we can't take more than two matrices at a time. We have to take two. Okay, so can I do this? Okay, so I can consider the problem like this. Okay, so the overall matrix product can be viewed as the product of this subsequence and this subsequence. So if this is a subsequences, these are the subsequences, first and second, then the number of alternative parenthetizations in this subsequence, okay, can give us P of, K, right? So this is the number of parenthetizations of the subsequence A1, A2, A3, dot 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 AK, first K number of matrices. Okay, and and what about the remaining? The remaining is P of remaining number of matrices n minus K, right? Okay, so if you consider this subsequence parenthization, we will have the number of parenthetizations in the first subsequence as Pk, and the number of parenthetizations in the second subsequence is Pn minus K. And as these two are simultaneous event, you have to product them, Pk into Pn minus K. Okay, that means this is P into P n minus K. Okay, right. Somehow this is, now this is for a single K. Single K means where we have splitted the overall sequence into two subsequences, where, so between the matrix AK and the matrix AK plus 1. And what is the value of K? K may be here 1. Here I may split the overall sequence into two subsequences. First sequence is consisting of the single matrix A1. The second subsequence may consist of the remaining n minus 1 number of matrices. K may be equal to 2. That means this could be my first sequence and this will be the second sequence. That means here 1 less than or equal to K less than n. Okay, because first sequence can't be this one, the overall sequence. There is no subsequence possible. Minimum, maximum, I may take this one, A1, A2, A3, dot dot dot, An minus 1. So n minus 1 is the maximum value of K. That means K less than n. Okay. So this product is for single K, and we have to sum up. We are calculating total number of parenthetizations. That means we have to sum up this product for all the possible values of K. K equal to 1 to n minus 1, and hence this formulation becomes summation over K equal to 1 to n minus 1. Okay, And from this model you can simply understand that it is nothing but a recursive problem. Okay. And just for your information, we do not want to explore and understand, just for your information, that applying brute force will take uh, either omega of 4 to the power n n to the power k. Okay, here n to the power by 2 by 2 or omega of 2 to the power of n. Okay. Okay, so which is an exponential term, either 2 to the power n or 4 to the power n by this one. So which is which is taking a lot of time. Okay, so that's why we have to go for some good method like dynamic programming or some other, maybe branch and bound backtracking. Okay, so already it's 10:19. So just I want to wrap up with this. In the next class, we will continue to develop the algorithm and see an illustrative example. Okay. So now coming to modeling the problem as a dynamic programming solvable problem. Okay. Okay. So let a I to j denotes, you know, the denotes the matrix product a1 dot a2 dot a j. This is not a1, this is I. ai dot uh, I plus 1. In suffix we have ai plus 1. So this is the matrix product aj. Now if I is less than j, then any parenthization of any parenthization of aij will actually do what? Will split the sequence. Okay, will split the sequence of product or the product, okay, between uh, product between ai ak and suffix k and a k plus 1. So this is important, where we have understood that. So 1 less than or equals to k, then uh, this is not 1, this is I. Okay. So now the problem becomes finding the optimal parenthization for this Aij becomes a problem of finding suboptimal, okay, parenthetizations of uh, AK and AK plus 1. Okay. So an optimal parenthization, is equivalent to finding minimum cost problem, okay, while performing the products A in suffix I to j, A suffix I to j. Okay. So we want to understand where cost is, okay, where cost of A I to j is equal to the cost of A I to k plus cost of A 1 to j, plus 1 to j. Okay. And once you get this product AIK and AK plus 1 to j, then you have to multiply these two products AIK and AK plus 1 to j. So this matrix product, so cost of A suffix right, so plus cost of product suffix I 2k dot A k plus 1 pointing j. Okay. And then what we want to do, that is we want to now understand, this is the definition of the cost. Okay, now we want to understand what will be the cost of this product, and there is every inch of this the problem, there is a very good logical concept. So you, if you can understand everything and digest, your logical skill will be automatically enhanced and developed. Okay. So the cost of product. Okay, what is AIK? Let's try to explore what is AIK. So I mean, the problem demonstration is not so tough. It's very easy to understand. But as we are trying to develop the algorithm, we must understand all of this. So AIK is equivalent to is basically A1 into AI into A suffix AI plus 1 into A suffix A suffix I plus 2 and dot 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 A, the last suffix of A is K. This is AIK. And what do you mean by A K plus 1? This is K plus 1 2J, and that is K plus 1 dot 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 K plus 2, okay, dot K plus 3, and then dot 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 up to J. Okay, so these are the matrix product, these are the expansion. So now if you and just I want to draw here, this is having dimension, this is having dimension, this is having some dimension. Okay, so this is having some dimension. Similarly, this will have its own dimension. Similarly, this is, and finally this is. What is happened to this one? In suffix it is G. Okay, so what we have here, the dimension of this is P suffix, as it is AI is having dimension P I minus 1 cross, not here, cross P suffix I, dimension of AI. Similarly, the dimension of AI plus 1 is P I, then P I plus 1. Okay. Similarly, we have dimension of AK is P A minus 1. Just if you can't understand, if you are having any problem, just please ping me. So into suffix K. So if you multiply these matrices consecutively, so AI minus, see, Pi get cancelled, Pi plus 1 will be cancelled with while multiplying AI plus 2 and dot dot dot. So Pk minus 1 would have been cancelled with the previous matrix Ak minus 1. So the remaining dimensions left, which are Pi minus 1 and Pk. So this overall product Aik will be of dimension Pi minus 1 and Pk. So this is important. Okay. So here we want to extend further. So it's a dimension. Let me get over here. So dimension A suffix I2k, which is having a dimension P I minus 1 cross P K. This is important. Similarly, we have here, uh, you can similarly find out the dimensions of AK plus 1, which is P K cross PK plus 1. This is PK plus 1 cross PK2, PK plus 2. This is PK plus 2 cross PK plus 3. And the last dimension will be Pj minus 1 Pj. And after producting, multiplying all these matrices, the first dimension which will be left is Pk, and here it is Pj. Okay, so that we can write here. So here that is A in suffix. I am about to close. Yes, already is getting late. So Pk plus 1 pointing J. Okay, so this should have a dimension, P suffix K cross P suffix J. So these are the dimensions available now after producing product A I to K and product A K plus 1 to J. And now you are producting these two, multiplying these two matrices. All their dimensions are Pi minus 1 cross Pk and Pk cross Pj. So after multiplying them will involve the number of scalar multiplications is Pi minus 1 into Pk into Pj. So this cost of product, this is nothing but Pi minus 1 into Pk into Pj. So hence in the next line we have the cost definition. Revised cost definition is here, that is P suffix K minus 1. Is it K minus 1? I minus 1. Sorry, I minus 1. Then P suffix K, then P suffix J. So this is the revised cost by computing Aij product. Cost of Aik, cost of Ak plus 1 to J, and Pi minus 1 Pk Pj. This is the revised, this is the final model or formulation of the cost. Okay, so on the basis of this cost function, we will try to optimize. This sub-optimal. We want to optimize the parenthization. The parenthization is nothing but is viewed as two suboptimal parentheticals. So how can we solve a suboptimal parenthization problem? By minimizing this cost. Okay, so I'm done with today. Already is getting late. Any query?
Sir, can you repeat the last line by minimizing the cost?
Right. So see, the overall subsequence is viewed as the overall sequence P is viewed as a problem of two subproblems. Okay, so you have to divide the sequence into two subsequences. Subsequence 1, first subsequence, and second subsequence. Okay, so I wanted to find out the optimal parenthization of the main given sequence P. Now the problem becomes, once I divide or split the main sequence into two subsequences, subsequence number 1 and subsequence number 2. In our case, the first subsequence is AI2K product, and the second subsequence is corresponding to AK plus 1 to J product.
J.
Right. So now what is the optimal parenthization for ai to k and the optimal parenthization for a k plus 1 to j. And how can you compute the optimal parenthization? Finding the optimal parenthization means finding the minimum cost. The parenthization which will lead us to minimum cost means what is the minimum cost? What is the cost definition? Cost is nothing but the total number of scalar multiplications involved in that parenthization. So optimal parenthization means that parenthization which is giving us an optimal order of matrix multiplications which will lead us to minimum number of scalar multiplications. So you optimize ai to k, then optimize a k plus 1 to j, okay, then you optimize the overall sequence a I to j. So this is the meaning. Sir, a1, a2, a3 in this case, p3 equal to o. That is very simple. Uh, um, right here. So while having three matrices a1, a2, a3, and we have a1 into, first we compute a2, a3. So one parenthesis we have for a2, a3. Once I got the product a2, a3, then that product is multiplied with a1. So total two parentheses are required for this p3. Oh, yes, you may argue that, sir, why you have written here p3, p3 and p3 becomes 4. Let's say this is p1, 3, this is p2, 3. Okay, so p1 means this is the p1 sequence. This is the p1 sequence, p1 parenthesization, and this is another parenthesization combination, arrangement. Okay, so for p1 parenthesization we have number of parentheses equal to 2, and for p2 sequence we have parenthesization equal to 2. So total parentheses is p3 equal to p1 plus p2, that is 2 plus 2 equal to 4. If you consider four matrices similar to that what we have explained over here, these four matrices, okay, and then you know here number of parentheses is equal to 1, 2, 3. Here also 3, here also 3, 3, 3, 3, right? So 3 into 5, 15. So total number of parentheses here equal to 15. Okay. So that is the meaning of total number of parentheses, Pn. And Pn is nothing but is following a recurrence relation. And also even here what we have found, we have modeled the cost function, which is nothing but a recurrence of costs, okay, of two sub sequences or sub matrix products ai to k and a k plus 1 to j, right? Any other query? Yes, so please review the video again, because this topic will require some time. So invest some time. Please invest some time on this topic. It's a very slow process topic. You can't go faster. Okay. Okay then. Thank you. Good night.